We begin in a very quiet place, a place with no wind, no voices, no distant hum of activity, just space, wide and open, stretching in every direction. If you imagine yourself floating there, far from any planet, far from any star, you might expect to hear something. After all, the universe is full of things: stars burning, galaxies turning, planets moving in quiet orbits. It feels like there should be sound, some deep background noise, some constant signal. But there is none. The universe, as we experience it, is silent. This silence can feel surprising, because our everyday life is never truly quiet. Even in the calmest room, there is always something, a faint vibration, a distant sound. Our world is filled with air, and air carries sound. Every movement creates a ripple. Every ripple travels, and we are used to hearing it. So when we think about space, we often carry that expectation with us. We imagine explosions echoing, stars roaring, cosmic events making noise across the void. But this is not how it works. In space, there is almost nothing to carry sound. Sound needs a medium, something like air, or water, or solid material. Without that medium, sound cannot travel. It fades immediately. This is why space is silent. Not because nothing is happening, but because there is nothing to carry the sound of it. And yet, this explanation only answers part of the feeling. Because when people speak about the universe being quiet, they often mean something deeper. Not just the absence of sound, but the absence of signals. The absence of clear signs that something out there is reaching back. We look into the night sky, and we see stars, thousands of them, even millions with the right instruments. Each one is a sun, many with planets. Many of those planets exist in conditions where life could be possible. And yet, when we listen, carefully, patiently, we do not hear voices. We do not see obvious signs of activity. We do not detect clear messages crossing the vast distance. This creates a quiet of a different kind. A quiet not of sound, but of presence. It is the quiet of an unanswered question. A question that has been asked in many forms. If the universe is so large and so full of possibility, then where is everything? This question does not need to be rushed. It does not need a quick answer. It can sit gently in the background, like a distant thought. The universe itself moves slowly, on timescales far beyond human life. Stars form over millions of years. Galaxies evolve over billions. Even light, the fastest thing we know, takes time to cross the distance between stars. So the quiet we notice may not be emptiness. It may simply be distance and time. When we look at a star, we are not seeing it as it is now. We are seeing it as it was years ago, sometimes thousands or millions of years ago. The light has been traveling all that time. In a way, the universe is always slightly out of sync with us, always just beyond immediate contact. This adds to the sense of quiet, because even if something is happening far away, we may not know it yet, or we may not understand it when we see it. There is also the question of scale. The universe is not just large, it is vast in a way that is difficult to fully imagine. Our galaxy alone, the Milky Way, contains hundreds of billions of stars, and there are hundreds of billions of galaxies beyond it. With numbers like these, it feels natural to expect activity. It feels natural to expect noise, some kind of signal. But expectation is shaped by human experience, and human experience is very limited. We are used to environments where life is dense, where communication is constant, where signals are everywhere. The universe does not necessarily follow those patterns. It may be that life is rare, or distant, or quiet in ways we do not yet recognize. It may also be that we are still learning how to listen, learning what to look for, learning how to interpret what we find. This idea that the universe is quiet is not a conclusion, but an observation, a starting point, a gentle curiosity. We notice the silence, and we begin to ask why. The question itself becomes part of the experience. It invites patience and careful thought. It reminds us that not everything reveals itself quickly. Some answers take time, and some may remain open. As we continue, it helps to stay with this quiet feeling, not as something empty, but as something spacious. A space where ideas can move slowly, where questions can rest without pressure. And in that space, we can begin to look more carefully at what we mean when we say the universe is quiet. When we say the universe is quiet, we often imagine silence, like the absence of sound in a still room. But this kind of silence is only one part of the idea. To understand it more clearly, we can separate two different things: sound and signals. Sound is something very familiar. It is a vibration moving through a medium, usually air. When you speak, your voice creates tiny changes in pressure. These changes travel outward and reach another ear, where they are heard as sound. This process needs something to travel through. Without air, or water, or solid material, the vibration has nothing to move across. In space, there is almost no matter. The distances between particles are very large, so large that vibrations cannot pass from one to another in a continuous way. This is why even very energetic events, like a star exploding in a supernova, do not produce sound that travels across space. The energy is there. The event is real, but the sound does not carry. So, in this sense, the universe is silent because it lacks a medium for sound. But this is only the first layer. There is another kind of not hearing that is more subtle. Even without sound, the universe is not empty of information. In fact, it is filled with signals. Light, for example, travels through empty space. It does not need a medium. It moves as an electromagnetic wave. The light from distant stars reaches us after long journeys, carrying information about those stars, their temperature, their motion, their composition. All of this is encoded in the light and can be studied. This means the universe is not truly silent in an absolute sense. It is active, constantly sending out streams of information. We can think of this as a different kind of sound. Not something we hear, but something we detect. Instruments can receive these signals and translate them into data. Telescopes observe visible light. Radio telescopes observe longer wavelengths. And other instruments detect X-rays or gamma rays. Each type of signal reveals a different part of the universe. Each one adds detail. So, when we describe the universe as quiet, we are not saying there is no activity. We are saying something more specific, that we do not detect certain kinds of signals. Signals that stand out. Signals that seem intentional. Signals that might suggest communication. This distinction is important because it changes the meaning of the question. The universe is not silent in every way, but it can feel quiet in a human sense. We do not hear voices. We do not receive clear messages. We do not see obvious signs of technology beyond our own. This kind of quiet is not about physics alone. It is also about expectation. We expect patterns we recognize, signals that resemble communication as we understand it. Structured, repeated, meaningful in a familiar way. But the universe does not have to match those expectations. Signals could exist, but in forms we do not yet recognize. Or they could be too faint, too distant, or too rare to be easily noticed. There is also the question of interpretation. Even when we receive signals, we must understand them correctly. Natural processes can create complex patterns. Pulsars, for example, emit regular pulses of radio waves. When they were first discovered, their precise timing was unexpected and briefly considered as a possible artificial signal. But over time, they were understood as natural rotating neutron stars. This shows how careful we need to be. The universe can produce signals that appear structured, without any intention behind them. So the quiet we experience is partly a filter, a boundary between what we detect and what we understand. It is shaped by our tools and by our knowledge. As those improve, the sense of quiet may change. New instruments can reveal signals that were once invisible. New theories can help us interpret what we observe. But for now, the universe still feels quiet in a specific way. Not empty, not inactive, but lacking the kinds of signals we instinctively look for. This leads naturally to a deeper question. If signals can travel across space, and if the universe is full of stars and planets, then why do we not detect clear signs of others? Why does the sky remain so still when we listen for something familiar? For a long time, humans have not only looked at the sky, but also listened to it. Not with ears, but with instruments. Carefully built, carefully tuned. These instruments are designed to detect signals, especially radio waves, which can travel across vast distances. This way of listening is called radio astronomy. It allows us to observe parts of the universe that are invisible to the eye. Large dishes, sometimes spread across wide landscapes, collect faint signals from space. Each signal is very weak, often buried in noise. But with time and careful analysis, patterns can emerge. Some of these signals come from natural sources: stars, galaxies, and clouds of gas. Others come from more unusual objects, like pulsars, which emit regular pulses, or quasars, which shine with enormous energy. All of these create a kind of background activity, a quiet hum of information. But beyond these natural signals, there is another kind we have searched for. Signals that might be artificial, structured in a way that suggests intention. This idea led to the creation of SETI, a long-term effort to detect signs of intelligent life beyond Earth. SETI does not assume what such signals would look like, but it often focuses on patterns that stand out from natural noise. For example, a narrow-band radio signal, concentrated at a specific frequency. This kind of signal is rare in nature and could indicate a technological source. Scientists have scanned the sky for such signals for decades, pointing radio telescopes at nearby stars and distant regions of the galaxy. They record large amounts of data and analyze it with increasing precision. As technology improves, the search becomes more sensitive, able to detect weaker and more distant signals. There have been moments of interest, brief signals that stand out. One well-known example is the WOW signal, detected in 1977. It appeared as a strong, narrowband radio signal, lasting for a short time. It was unusual, and it drew attention. But it was never detected again, and its origin remains uncertain. Moments like this remind us that the search is complex and often inconclusive. Most of the time, the signals we detect can be explained by natural processes. Noise from space, noise from Earth, interference from human technology. All of these must be carefully filtered out before any signal can be considered unusual. This makes the search slow and patient. It requires both precision and restraint. So far, no signal has been confirmed as evidence of extraterrestrial intelligence. This does not mean such signals do not exist, only that we have not clearly found them. The universe continues to send information in many forms, but none that clearly answer the question we are asking. This creates a particular kind of quiet, a quiet shaped by effort, by careful listening, and by the absence of a clear reply. We are not simply waiting, we are actively searching. And yet, the result remains the same. No confirmed message, no clear signal, no unmistakable sign of another technological presence. This situation has led to deeper reflection, not just about our methods, but about the nature of the universe itself. If the conditions for life exist in many places, and if time has allowed for development, then why does the sky remain so quiet when we listen this way? This question does not demand urgency. It can unfold slowly, just like the search itself. And as it unfolds, it leads us gently toward one of the most well-known ways of framing this mystery. There is a simple question, often asked in a quiet way. A question that does not need complex language. If the universe is so large and so full of stars, then where is everyone? This question is known as the Fermi paradox. It is not a formal paradox in the strict sense, but it feels like one. Because two ideas seem to sit side by side, without easily fitting together. The first idea is about scale. The universe contains an enormous number of galaxies, each with an enormous number of stars. Many of these stars are similar to our Sun, and many are older. Around these stars, planets are common. This has been confirmed through observation. Some of these planets exist in regions where temperatures could allow liquid water, a condition often associated with life. From this perspective, it seems reasonable to expect that life could arise in many places. And given enough time, some of that life might become complex and possibly technological. The second idea is about observation. When we look and listen, we do not see clear evidence of such civilizations. No confirmed signals, no visible structures, no direct signs of activity beyond natural processes. The sky remains steady and largely unchanged. These two ideas together create tension, expectation on one side, and observation on the other. The Fermi paradox is simply the space between them. It does not claim a contradiction must exist, only that something is missing from our understanding. One way to think about it is to imagine time. The universe is about 13.8 billion years old. Our planet formed much later, and human technology is very recent. If other civilizations formed even a little earlier, they could be far more advanced. Over long periods, they might explore, expand, or leave detectable traces. Yet we do not clearly see such traces. Another way to think about it is distance. Even if civilizations exist, they may be very far apart. So far that interaction is rare or slow. Communication across thousands of light years would take thousands of years. A signal sent long ago might not have reached us yet. Or our own signals may not have reached others. There is also the idea of rarity. Life may not arise easily. It may require a sequence of conditions that do not occur often. Even if simple life is common, complex or technological life may be much less so. In this case, the quiet would not be surprising. It would be expected. The Fermi paradox does not choose one explanation. It allows for many possibilities. Each possibility changes the meaning of the silence. It could be a silence of distance, a silence of time, or a silence of rarity. It could also be a silence shaped by our limitations, what we are able to detect, and what we are able to understand. This makes the question gentle, rather than urgent. It is not asking for a quick answer, but inviting careful thought. The universe does not rush, and neither does this question. It sits quietly, alongside the stars, present but not demanding. As we stay with it, we begin to notice that the answer may not be a single idea. It may be a combination of many factors, each contributing a small part. To explore that further, it helps to look more closely at how likely life itself might be. To think about how common life might be, we can begin with something simple. Not a final answer, but a way of organizing uncertainty. This idea is known as the Drake equation. It is not a single number, and not a fixed prediction. It is a framework, a way to break a large question into smaller parts. Each part represents a step, from stars to planets to life, and eventually to detectable civilizations. We can move through these steps slowly, without rushing to conclusions. The first step is about stars. How many stars form in a galaxy like the Milky Way? Each year, stars are the starting point because planets form around them. The next step is about planets. What fraction of those stars have planetary systems? Observations now show that planets are common. Many stars host them. This part of the uncertainty has become smaller over time. Then we consider suitable environments. How many of those planets might have conditions that allow liquid water? This often depends on distance from the star and other factors like atmosphere. Some planets fall within what is called a habitable zone. Not too hot, not too cold. But even here, there is uncertainty because habitability depends on many details. Next comes the question of life itself. If conditions are suitable, how often does life actually begin? On Earth, life appeared relatively early, once conditions stabilized. This suggests it may not be extremely rare, but we only have one example. So the uncertainty remains. From simple life, we move to complex life, and then to intelligence. Each step may require additional conditions and long periods of stability. On Earth, complex life took billions of years to develop. Intelligence and technology came much later. This suggests that even if life is common, advanced civilizations may be less so. The final steps consider communication. How many civilizations develop technologies that send detectable signals, and how long those signals last? This last part is especially important because it introduces time. A civilization might exist, but only send signals for a short period. If that period does not overlap with our own, we would not detect it. This creates a kind of timing problem. Even if many civilizations exist across history, only a few may be detectable at the same moment. When all these steps are considered together, the result is not a single answer, but a range of possibilities. Some estimates suggest many civilizations. Others suggest very few. The difference comes from the uncertainties in each step. This is why the Drake equation is useful. Not because it solves the question, but because it shows where the unknowns are. It turns a large mystery into a series of smaller questions. Each one can be studied, slowly, carefully. Over time, some uncertainties become smaller, especially those related to stars and planets. Others remain wide, especially those related to life and intelligence. This uneven knowledge shapes our sense of the universe. We know more about where life could exist than whether it does exist elsewhere, and even less about whether it becomes detectable. So the quiet we observe may not be surprising. It may reflect these layers of uncertainty, each step narrowing the path, until only a few possibilities remain at any given time. This does not make the universe empty, but it may make it sparse. Sparse in a way that is difficult to notice from a single point. As we consider this, another idea begins to form. Not about how life begins, but about how it continues. Because even if civilizations arise, they may not last forever. Even if life begins, and even if it becomes complex, there is another question that follows quietly. How long does it last? Not just life itself, but a civilization capable of being noticed. This introduces the idea of fragility, not as something dramatic, but as something gradual. A civilization exists within conditions, environmental, biological, and technological. These conditions can change, sometimes slowly, sometimes more quickly. On Earth, life has continued for billions of years, but it has not been constant in form. There have been periods of stability and periods of disruption. Events like the Permian-Triassic extinction event and the Cretaceous-Paleogene extinction event show that large changes can occur. These events reshaped life on Earth, reducing diversity and altering ecosystems. And yet, life continued, adapting over time. When we think about civilizations, the timescales become much shorter. Human technological civilization is only a few hundred years old in its current form. The period during which we send detectable radio signals is even shorter. This suggests that the window of detectability may be limited. A civilization might exist for a long time, but only be detectable for a small fraction of that time. There are many reasons this window could close. Some are external, such as natural events. Others are internal, related to the development of the civilization itself. Technology may change. Communication methods may evolve. A civilization might move away from detectable signals, using forms of communication that are quieter or more efficient. In that case, it would become harder to notice. There is also the possibility of decline. Not necessarily sudden, but gradual. Resources may become limited. Environments may shift. Systems may become unstable. Over time, activity could reduce, and signals could fade. This does not require a single cause. It can be the result of many small changes, each one narrowing the ability to sustain large-scale communication. From a distant perspective, such a civilization would simply become quiet. Not gone in a dramatic sense, but no longer visible in the ways we can detect. This idea adds another layer to the quiet of the universe. It suggests that silence may not mean absence. It may mean that activity is brief or difficult to observe. If many civilizations arise, but each has a short detectable phase, then the chance of overlap becomes small. We might simply not be listening at the same time. This creates a kind of temporal distance, even between nearby stars. Not distance in space, but distance in time. A signal may have been sent long ago, before we had the ability to receive it. Or it may be sent in the future, long after our current methods have changed. In this way, the universe can be full of activity across time, and still appear quiet in any single moment. This perspective does not require rarity alone. It combines rarity with timing. Even common events can be hard to observe if they are brief and scattered. This makes the quiet feel less like a contradiction and more like a natural result of overlapping conditions. Conditions that must align for detection to occur. As we reflect on this, another factor becomes clear. Even if a civilization is active, and even if it is within its detectable phase, there is still the question of distance. Because the universe is not only shaped by time, but also by vast space between points. Distance adds another quiet layer, not through silence alone, but through separation. The universe is not just large, it is structured in vast stretches, with space between stars, and even more space between galaxies. These distances are measured in light years. The distance light travels in 1 year. Light moves very fast, about 300,000 kilometers each second. And still, it takes time to cross the gaps between stars. The nearest star system to Earth, Alpha Centauri, is over 4 light-years away. This means any signal traveling at the speed of light would take more than 4 years to arrive. And a reply would take just as long to return. A simple exchange, even between neighbors, would span nearly a decade. As we look farther, the delays grow much larger. Across the Milky Way, distances can reach tens of thousands of light years. A signal crossing the galaxy would take that many years to arrive. This creates a natural limit, not on possibility, but on interaction. Even if civilizations exist, they are separated by time as much as by space. Communication becomes slow and uncertain. Messages cannot be exchanged in real time. They move more like distant echoes, sent out and received long after they were created. This changes the nature of connection. It is no longer a conversation, but a sequence of isolated signals, each one separated by years or centuries. And this assumes that signals are strong enough to be detected, which is not always the case. As signals travel, they spread out, their strength becoming weaker over distance. This follows a simple pattern. The farther the signal travels, the more it disperses. By the time it reaches a distant star, it may be extremely faint, difficult to distinguish from background noise. Detecting such a signal requires sensitive instruments and careful filtering. Even then, only certain types of signals are likely to stand out. Narrow, focused, and sustained transmissions. But not all civilizations, if they exist, would necessarily send signals in this way. They may not aim signals toward us, or may not transmit at high power. Their signals could pass by unnoticed, simply because they are not directed in our direction. This adds another form of quiet, a quiet created by geometry. The paths that signals take and the positions of observers must align for detection to occur. If they do not align, the signal exists, but is never received. Distance also affects travel, not just communication. Moving across interstellar space requires enormous energy and long durations, even at speeds far beyond current human technology. Journeys between stars would take many years. At slower speeds, they would take centuries or longer. This makes physical exploration difficult and rare. Civilizations may remain near their home systems, not because they cannot expand, but because expansion is slow. Over cosmic distances, even a spreading civilization would take millions of years to cross a galaxy. This is long, even compared to the lifespan of many stars. So, while expansion is possible in theory, it may not be visible at any given moment. It may appear incomplete or too distant to notice. All of this contributes to a steady, quiet, not because nothing exists, but because everything is far apart, separated by space, and stretched across time. Signals fade, messages delay, paths do not always meet. The result is a universe that feels still, even while it is active. This perspective softens the question slightly. The silence does not require absence, only distance and limitation. And yet, even with distance, it is possible to imagine that some civilizations might choose not to send signals at all. Not because they cannot, but because they prefer not to be heard. There is another possibility, one that does not depend on distance alone. It begins with a simple thought. What if others are also quiet on purpose? Not absent, not unreachable, but choosing not to be easily detected. This idea is sometimes described as the dark forest hypothesis. It is a way of thinking about behavior, rather than physics. A way of asking how civilizations might act when they exist in a vast and uncertain environment. The core idea is quiet and simple. If you do not know who else is out there, it may be safer not to announce yourself. Space is large, but it is not completely empty. And information travels, even across great distances. A signal sent outward does not only carry content, it also reveals a location. It says, in a very basic way, something is here. If there are many civilizations, each with unknown intentions, then revealing that information could carry risk. Not necessarily immediate, not necessarily certain, but possible. From this perspective, silence becomes a strategy, a form of caution, not driven by fear alone, but by uncertainty. It is difficult to predict the behavior of others, especially across different forms of life. Different histories, different environments, different ways of thinking. Without shared context, intentions are hard to interpret. So a civilization might choose to limit its signals, to avoid unnecessary exposure. This does not mean complete silence, but rather controlled communication. Signals may be kept local or directed in specific ways. Instead of broadcasting widely, they may focus inward, using methods that are efficient but not easily detectable at great distances. This kind of behavior would reduce the chance of detection. Even if many civilizations exist, the universe could be active, but quietly so. Each civilization aware of its surroundings, but cautious about revealing itself. Over time, this could create a pattern, not of absence, but of mutual silence. A balance shaped by shared uncertainty. It is important to treat this idea carefully. It is a hypothesis, not a confirmed description. It does not claim that such behavior is certain, only that it is possible. And it depends on assumptions about risk, decision-making, and long-term strategy. These assumptions may not apply universally, but they offer one way to think about the quiet, a way that focuses on choice rather than limitation. There is also a softer version of this idea, one that does not involve risk. A civilization might simply not feel the need to broadcast. It may turn inward, focusing on its own development. Communication beyond its system may not be a priority. Or it may use technologies that are subtle, efficient, and difficult to detect from afar. In this case, the quiet is not protective, but natural, a result of how communication evolves. On Earth, some of our own signals have already become less detectable. Early radio broadcasts spread widely into space. But newer technologies often use more focused, lower power transmissions. Fiber optics, for example, carry information without radiating it outward. This trend suggests that detectability may decrease over time, even as technology advances. If this pattern is common, then many civilizations could pass through a brief phase of visibility, followed by a longer phase of quiet operation. This would make them harder to detect, even if they are present. So the quiet we observe may not be a lack of activity, but a result of how activity is expressed. Subtle, contained, and not easily visible across great distances. This adds another layer to our understanding. The universe may be quiet not only because of distance, or time, or rarity, but also because of choice. As we consider this, another question appears. Gentle and open. Even if signals exist, even if they are being sent, are we actually listening in the right way? When we listen to the universe, we do so with specific tools and specific expectations. We choose certain frequencies, certain patterns, certain kinds of signals to focus on. This helps make the search manageable, but it also creates limits. Because what we look for shapes what we find. Most searches for distant signals, especially within SETI, focus on radio waves. Radio waves are useful because they travel far and can pass through dust and gas. They can carry information and can be detected with large instruments. This makes them a reasonable place to begin. But it is still a choice. One option among many possible forms of communication. There may be other ways to send information, ways we do not yet use, or do not yet recognize as signals. For example, light itself can be used to transmit information in the form of pulses or patterns. Some searches look for laser signals, brief flashes that stand out against the background of stars. But these searches are limited, covering only small parts of the sky at a time. There are also signals beyond what we can easily detect, forms of energy or modulation that fall outside our current instruments. If a signal exists outside our detection range, it will remain invisible to us. This creates a quiet that is not physical, but observational. A quiet shaped by the boundaries of our tools. There is also the question of pattern. We often look for signals that are structured, repetitive, or mathematically simple. Patterns that suggest intention. But not all meaningful signals need to follow these forms. A signal could be complex, irregular, or embedded within natural noise. If we expect simplicity, we may overlook complexity. And if we expect patterns similar to our own, we may miss unfamiliar ones. This is a challenge of interpretation, not just detection. Even when data is collected, it must be understood. Large volumes of signals are recorded, far more than can be examined by direct human attention. So algorithms are used to filter, sort, and highlight unusual patterns. These algorithms are designed with assumptions about what is likely to be meaningful. If those assumptions are narrow, they may exclude signals that do not match expected forms. This creates another layer of quiet. Signals that are present, but not recognized as significant. There is also the issue of sensitivity. Instruments can only detect signals above a certain strength. Weak signals, even if structured, may be lost in background noise. As technology improves, this threshold becomes lower, allowing fainter signals to be detected. But there are still limits, set by physics and by the environment of observation. Interference from Earth, for example, can mask or mimic signals from space. This must be carefully filtered, adding complexity to the search. Another factor is coverage. The sky is vast, and observations can only focus on small regions at a time. Even large surveys leave much of the sky unexamined at any given moment. A signal could appear, briefly, in a region we are not observing, and then disappear. In that case, it would go unnoticed. This introduces a quiet shaped by chance, whether our instruments are pointed in the right place, at the right time. When all these factors are considered together, the quiet of the universe becomes more layered. It is not only about what exists, but about what we can detect, and how we interpret what we detect. The absence of clear signals does not always mean the absence of signals entirely. It may reflect the limits of our current approach. This does not reduce the value of the search, but it reminds us to remain open to new methods, new tools, and new ways of thinking. As our understanding grows, the range of what we can notice may expand. And with it, the quiet may shift, revealing patterns that were once hidden. For now, the universe remains quiet in the ways we currently listen. And this leads to another gentle possibility. Not about how we listen, but about when we are listening. Because the universe itself has a history and a timeline. And we exist at a very specific moment within it. When we look at the universe, we are also looking through time, not just across distance. Every signal we receive has traveled for a certain duration, carrying information from the past. This means we do not see the universe as it is now, but as it was, at many different moments. The universe itself has a timeline, a long history that began with the Big Bang, about 13.8 billion years ago. In its early stages, the universe was hot, dense, and simple. Over time, it expanded and cooled, allowing structures to form, first atoms, then stars, then galaxies. Planets formed later, around some of those stars. And life, as far as we know, appeared even later. This sequence takes time, billions of years. It suggests that the conditions for life, and especially complex life, do not appear immediately. They emerge gradually as the universe evolves. Our own planet, Earth, formed about 4.5 billion years ago. Life appeared relatively early, but complex life took much longer. Technological civilization is a very recent development. This places us at a particular point in the timeline. Not at the beginning, but not necessarily near the end. Some stars in the universe are much older than our Sun, which means their planetary systems could also be older. In those systems, life may have had more time to develop. But time alone does not guarantee outcomes. Conditions must remain stable, and many steps must align. There is also the idea that the universe may still be in an early phase for life. Not early in terms of stars, but in terms of complexity. Heavy elements, like carbon, oxygen, and iron, are created inside stars. These elements are necessary for planets and for life as we understand it. Over time, as generations of stars form and evolve, the abundance of these elements increases. This means that later periods in the universe may be more favorable for the development of life. In that sense, we may not be late, but relatively early. Early in a long unfolding process. If this is the case, then the quiet we observe could be temporary. Not a permanent feature, but a phase. A period before many civilizations emerge, or before they become detectable. There is also the idea of synchronization. For two civilizations to notice each other, their detectable phases must overlap in time. Even if many exist across history, they may be spread out, separated by millions of years. This would make direct detection unlikely, even if life is not rare. In this way, the timeline of the universe adds another quiet layer. A quiet shaped not by absence, but by timing. By when things happen, and how those moments align. We exist at one point, observing light from many others, but not necessarily sharing the same present. This perspective softens the question again. The universe may feel quiet, not because it lacks activity, but because we are early or slightly out of step, watching a process that is still unfolding. And as we sit with that idea, the quiet becomes less like a void and more like a pause. A pause within a much longer story. A story that continues, slowly, across time. And in that slow unfolding, the quiet itself can begin to feel different, less like something missing, and more like something that can be understood in a gentler way. After considering distance, time, rarity, and uncertainty, the quiet of the universe begins to feel different, not as an absence, but as a kind of space, a wide, open space where things unfold slowly. In everyday life, quiet can feel unusual because we are surrounded by constant input, sound, movement, information, always present. But in the larger universe, quiet may be the natural state. Not empty, but spacious. A place where events are separated and spread out. This kind of quiet allows structure to exist. Stars form in calm regions of gas. Galaxies rotate over long periods without disruption. Planetary systems remain stable for billions of years. These processes depend on balance, and balance often appears as stillness. Even on Earth, quiet environments can support complexity. Oceans, deep and steady, allow ecosystems to develop. Forests, growing slowly, create layers of life over time. In these places, quiet does not mean inactivity. It means processes unfolding without interruption. The universe may be similar. A place where most activity is gentle, extended, and not immediately visible. From this perspective, the absence of obvious signals becomes less surprising. It reflects the scale and pace of cosmic processes. Not everything happens in a way that stands out or draws attention. Many events are subtle and require time to notice. This can change how we feel about the question. Instead of asking why the universe is silent, we can ask what kind of quiet it holds. A quiet shaped by distance, by time, by the limits of observation, and by the possible choices of civilizations. Each of these adds a layer, creating a quiet that is complex, but not empty. There is also a sense of patience in this quiet. The universe does not rush toward outcomes. Stars take millions of years to form and billions to evolve. Life, where it exists, adapts slowly. Civilization, where it arises, may pass through phases, each step unfolding at its own pace. When we observe this from a human timescale, it can appear still. But this stillness is relative, a result of our position within the process. We are watching something very large and very slow. So the quiet becomes a kind of perspective, a reminder of scale. It shows how small our window of observation is, and how much may exist beyond it. Not hidden, but simply distant, or unfolding over longer spans of time. In this way, the quiet can feel steady, even reassuring. It suggests that the universe is not chaotic everywhere, but often balanced. Not filled with constant signals, but with processes that do not need to announce themselves. This does not answer every question, and it does not remove uncertainty. But it changes how the question sits, making it softer, less about something missing, and more about something unfolding. As we remain with this feeling, the quiet becomes part of the experience. Not something to solve, but something to notice. And in that noticing, the universe feels wide, open, and patient. A place where questions can remain without needing to close. As we come to rest with this idea, the question remains, but it feels lighter. Not a problem to solve, but something to sit with. The universe is quiet, and we have moved through many ways of understanding that quiet. We have seen that space does not carry sound, that signals can be faint, distant, or difficult to recognize. We have considered that life may be rare or widely separated, that civilizations may be brief or careful, that time itself may keep events from overlapping. Each idea adds a small piece, not a final answer, but a gentle outline. When placed together, they do not remove the quiet, but they give it shape. A quiet formed by distance, by timing, by limitation, and by possibility. It becomes something that can be understood slowly, without needing to be resolved. If we imagine looking out into the night sky, the stars remain as they are, steady points of light, each one distant, each one part of a larger structure. We do not hear them, and we do not receive clear messages from them. But they are not empty. They carry information, history, and potential. Light travels from them across years, sometimes across thousands of years, reaching us quietly, without sound, without urgency. In that sense, the universe is not silent, but softly speaking in a language we are still learning. A language of light, of motion, of gradual change. And we are listening, in our own way, with instruments, with observation, with patience. This listening does not need to rush. It can continue over time, growing slowly as our understanding grows. The quiet does not close the question. It keeps it open. It allows space for new ideas, new methods, new ways of noticing what is already there. Perhaps signals will be found, or perhaps the quiet will remain. Either way, the universe continues, unfolding without pause. Stars forming, planets moving, light traveling across distance. All of it happening, whether or not it is observed. And we are part of that process, observing, asking, and learning slowly. So the quiet becomes something we share, not something outside of us. It is part of the same universe we are made from. The same processes, the same materials, the same long passage of time. As the thought settles, it does not need to conclude. It can remain open, like the sky itself. Wide, quiet, and still continuing.